declarative programming languages have several advantages over traditional languages. For example, programs in such languages are considerably shorter than the equivalent programs in imperative languages. Here, for example, is a program in C. And here is the equivalent program in Erlang. Hello.
Hello, Joe.
Hello, Mike.
Hello, Joe. And I'll make a call to Robert.
Hello, Mike.
Hello, Robert.
Hello, Mike.
Hello, Joe.
Well, first of all, I'd like to say thank you very much for inviting us to this conference. We're honoured to be here. The last time that Joe, myself, and Robert, or the other way around, gave a talk was in fact that movie. I think that's the last time we've actually given a talk together, was it not? We haven't been practicing since then, and we've made some mistakes. But I was asked to give a title for this talk some time ago, and I talked to Joe, and I said, well, can't we just say how long we've been programming? And we tried to work that out. We came to it was 183 years that our combined programming experience was. Here we all are. The first thing to notice is that functional programming has weird effects on the colour of one's hair. That we noted that yesterday in the keynote as far as Haskell was concerned, that the authors of Haskell's hair has also changed colour during the time. I think it must be something to do with programming. But here we all are. I like that picture myself. It's a lot nicer than it is nowadays, but never mind. The other thing was that when I said 183 years, I think we got things slightly wrong. I think we added up our ages instead of added up the other. So this is actually that I've been working at it for 45 years. I could go on talking about paper tape and hole cards and punch cards and all the rest of it, but I won't bore you with that. This is the number of years. Actually, it's about 122 years, which I still think is a fairly impressive total. But after that sort of some fundamental error in specification, I hope you trust us that we can actually write code. I thought I'd tell you a bit about the history. Why did the Erlang happen? Or what was it all about? Well, years and years ago, or not years ago, about 1978, the first AXE telephone exchange was introduced. You all have used AXE telephone exchanges, even though you don't know it. In fact, the whole of the BT network is based on them nowadays, although they've gradually been phased out. It required an enormous effort to write the software for these exchanges. In fact, that nowadays the effort seems fairly small. When it started, I think there were about 100 people writing code. Nowadays, for a 3G or 4G system, we actually can sort of say that it's close to 1,000 people. So the situation hasn't actually got any better. But in the days that we started writing code for telephone exchanges in a weird language called Plex, it took a large effort to do that. And we were asked, since you're computer science people, or we thought we were computer science people, the definition of what computer science was then wasn't very specific. They sort of said, can you actually do something to make this easier? And I think they thought that we would actually do something to make Plex easier and to make the program of AXE10 easier. We misinterpreted what they said and said that we would actually do something different. Well, basically we had to make something which did exactly the same as AXE10. And on this side of the picture here, you can see a sort of schematic diagram of what it was. For a start, there were masses, thousands of transactions at the same time. As you can imagine, in any telephone exchange, you would have thousands of transactions, and the transactions, as such, are fairly small. That when programming these things, they found that in the previous version of the first exchange, which was controlled by software, Ericsson, it was called AKE, there was an enormous amount of pointer errors and array bounds errors and that sort of thing, which is a sort of what you get with this sort of programming. So that AXE was actually very clever. They introduced something in the middle which you see is called the reference memory, and this is a very fine-grained MMU. So you're actually doing sort of bounds checking and a pointer checking in hardware, which is, I don't think I've ever seen that done anywhere else. Maybe it's been done anywhere else, but there are no wide pointers. The other thing you can do, because you've got that hardware between yourself and the memory, you can actually move things around. It's like a sort of a hardware-controlled garbage collection and compactifier, if you like. Although we didn't know what garbage collection was then, I suppose. You can rearrange memory, you can do all sorts of things. The other thing is, of course, a telephone exchange, you can't take it down. I mean, people like to phone the 111, the 112 numbers or the 999 numbers or whatever, the emergency numbers at any time. You can't sort of say, sorry, we've taken the exchange down for maintenance. So being able to change code at runtime without stopping an exchange was actually vital and is still vital. If you have hundreds of programmers programming these sort of things, you have to have some sort of modular system. You have a system where various people can write different parts independently from each other, and you have to be able to handle the different parts separately. The other thing, of course, is that in the days when this sort of system was made, the major faults we had were actually in hardware. We had memory errors and this sort of thing, so we had to be able to recover from that sort of error. Of course, there were software errors as well, and you can't stop a telephone exchange working because you hit a bug. You have to recover for it in some sort of way. Recovery in telephony is actually very easy because you just simply abort the call and you hope that people can remake the call. The job we got was do the same thing as in AXE, but please, can you use conventional processors? Making your own processors, no special purpose hardware, is very expensive. Could you please use some sort of standard operating system? I think they probably at that time thought we were going to try and use some IBM systems, but we all hated IBM, so we didn't use them. We did some with Unix. Another problem we had was the processors were weak, and the idea that you could actually get more capacity by putting more processors into the problem was something which came along. And they said, well, could you make it scalable? Could you, if we don't have enough power, could you please just add a few more processors so we get power? The interesting thing about this is that all these requirements are sort of obvious requirements for the sort of world we have today. That we ended up doing this sort of thing, and for example, the requirements for scalability just fits very well with multi-core processors and cloud processing. So a lot of things that happened at the time actually guided us in the right direction. I don't think we knew that multi-cores were about to turn up, but they did. And then significantly, the last thing was that we were asked to make development efforts significantly easier. In other words, do it with 5 people instead of 100. The important thing here to realise is that hardware changes the way we think. That I'm sure that a lot of you have, well, maybe none of you are old enough, can remember to do overlay processing in MS-DOS, where you sort of swapped in pieces of code to get things working. That sort of processing, the way you actually program things, is very much determined by how much memory you've got, and that you're always online changes the way you think, that we now have a network, that we have faster CPUs which changes the way you think. We can do things more inefficiently than we used to do before. We can have larger software. Mobility, that we can actually move around, changes the way we actually program. And if the hardware doesn't change, the software doesn't change. I mean, the way most people program, and I'm not really talking about people sitting in this room, but if you look at the world in general, the way people program, it hasn't really changed significantly since the 80s. People are still using C, they're still using C++, so they're still using Java and languages like that. It hasn't actually significantly changed. So hardware didn't change very much until about 2004 when multi-cores turned up. I think, Joe, this is you.
Yeah, a bit earlier, actually.
Was that? I think, okay, sorry.
You were doing such a nice job, I didn't want to. Yes, right. So the title of the talk was 183 years of experience, which was then downgraded to 122 years. And so towards the end of the talk, I was going to kind of sum up what's happened during this period we've been programming. So one of the theses I have, and to trying to make sense of it, is that if the hardware doesn't change, the programming languages aren't going to change much. Because, okay, the way we describe things using that hardware might change, but the fundamental changes are going to be caused by scale changes in hardware. And I'm going to look at those scale changes and see what happens. And basically, between, I reckon, you know, the mid-80s to about 2002, hardware didn't really change that much. Okay, the clock rates got faster and we got more memory, but they're still von Neumann machines. They didn't become parallel, they didn't become distributed. We still had single systems. And since then, we've seen things like mobility, we've seen things like being always online, and they are enablers of the cloud and things like that. The cloud wouldn't be a possibility if you weren't always connected to the network. So, I mean, the cloud follows being always connected to the network. So, I want to look at some of those changes as we go along. So I'm going to go back to about 1980, and this was the state of the world when we started solving the sort of problems that I was talking about. We had a machine with a 3 megahertz clock, a VAX 11750. Well, now machines have got a 3 gigahertz clock. That's a factor of 1,000 faster. We had 4 megabytes of memory. Well, a machine today will have 4 gigabytes of memory, so that's a factor of 1,000. So, and they will disagree with me. I reckon this little thing I have in my pocket is 15 million times more powerful.
That's not.
Sorry. But you'll certainly agree it's 1,000 times faster.
It's 1,000 times
faster.
faster.
It's got you know, maybe 1,000 times more memory. So the machine we developed Erlang on is 1,000 times more powerful than this. So if you think this is a weak computer, forget it. It's a really powerful machine.
Jolly fast, Joe.
Jolly fast. We haven't actually figured out what we... And now we've put these things in everybody's pockets, and we'll be able to communicate up to a gigabit per second in a few years, and we'll put a terabyte of memory in them, and we'll have a petabyte of memory in them within 20 years. And we have to ask, what are we going to do with these things? And that's quite exciting. So let's go back to 1984. This was the problem. I'm not going to read out all of those things, but it's a long list of what we wanted to achieve. It was written in a paper by Bjarne Dekker, who's our boss. He wrote this paper in 2000. I'm not sure if it's a sort of reconstruction of what we did. I had an argument with Mike and said, yeah, well, you know, we knew what we were doing at the time. I'm not so sure we did know what we were doing at the time, but we certainly knew we wanted to distribute things over lots of computers. We didn't really know how to do this, and we wanted fault tolerance. And these kind of, I mean, does anybody have computers that they want to change the code while they're, you know, without taking them out of service? Does anybody want to do that? Right. Does anybody worry if their system's out of service? You know, does anybody want to have millions of people? Does anybody want to distribute their application? Well, there's a long list of those. If you're interested in any of those points and want to do that today, well, that's what we were interested in you know, around about 1984, 1985. So we started looking at those problems. And why were we looking at them? Because we were working for a telecoms company, and we had the hardware that could do this. So people haven't had hardware that was connected together until about 2004, 2005. So people didn't start becoming interested in distributed programming as a practical thing until they had it in their households. When you first got your ADSL or your permanent linked line at home that gave you megabit per second, you know, then you could write distributed programs. And then things like BitTorrent appeared, and people started sharing files, and the Wikipedia appeared, and WikiLeaks, and all these kind of things appeared because the technology had enabled it. Well, we had that technology in about 1984, 85. So we had a bit of a head start on the people who discovered that a few years ago. Okay, so that's really why I think Erlang is kind of well positioned, because we've been looking at those problems for a very long time. And we also had kind of reality. You know, we worked in an industrial environment as opposed to an academic environment. So we weren't really interested in kind of inventing new science or doing anything wonderful in a scientific sense, but we were interested in stealing ideas from academics and things and trying to shove them into products. And this good lady is Erlang, and she was project manager, I guess you'd call it, of a project that wanted to make a new telephone exchange. And this is back in 1986. I made this slide for ICFP, a functional programming language conference, just show the sort of timeline. And we're kind of divided into things that happen, that these are things you have to do in order to make a programming language. You see, okay, if you're an academic, you're perhaps looking at the theory of type theory or something like that, but if you want to get something out and you want to get users, you have to participate in a lot of different things. You've got to do academic things, you know, you've got to make it work, you've got to implement it, obviously, so it works. But you've also got to do a bit of marketing and try and sell the idea to people. You know, we have, on occasion, hundreds and hundreds of sort of presentations of what Erlang is inside Ericsson, just to be told to bugger off, you know, it'll never work, and off you go. So how did it go? Well, they told us to bugger off, so they didn't actually sort of throw us out physically, so we'll go back in 6 months and see what happens. So
I got thrown out.
Good bit of optimism is.
Yes.
So a good measure of optimism is kind of, if you try and flog a new technology and they say, no, bugger off, you know, you just go back in 6 months and smile at them a lot. It's a good thing to do. And then, during this time period, we also changed technology quite a lot, because how we implemented things back in the mid-80s changed. We started off with Prolog as an implementation language, and then that changed, and we'll talk about that later. And then, at the same time, we were always doing this thing with users and with products, and I think that's interaction very helpful. So this was reality for us in about 1985. This is an MD 110. And that was the first hardware that we got to control. And as Robert said, hardware is funny. You know, I mean, it breaks your nice theories. If it doesn't work on the hardware, your theories were wrong. It's a reality check. And so this was where theory met practice. And this woman, Erlang, I think, we're trying to program this thing in a better way than had been done before. So we set up a target, and basically we decided, okay, we knew how to program it, and we would go ahead and write the software. They would write software, and we would improve Erlang so that the performance went up. We reckoned it would take them 2 years to make the product, and it would take us 2 years, 3 years, and it would take us 2 or 3 years to improve the performance of Erlang to the point where we could ship it as a product. And this actually did become a product, and it was sold to the European Parliament, and still probably controls all it's a local PAVX, which politicians use to talk to each other. And, well, so Erlang had, this is the first version of Erlang, because Erlang wanted a way of describing telephony, and I suppose you could say, to start with, Erlang was a domain-specific language for describing telephony, and we had to make it attractive to Shersten. Of course, it can be, because the telephony problem is very similar to other problems, it's not just telephony. I mean, thousands of people code change on the fly. That's a characteristic of many problems, although we didn't realise it at the time. And Shersten wanted to program it like this, because she had something that looked like this. These are fishbone diagrams. And Shersten wanted to program in fishbone diagrams, because she called them fishbone diagrams. You can't see that, so I've blown it up. And that's a fishbone diagram from about 1983 or something. But it's a domain-specific language for describing telephony. And it says, if you're waiting for it, this is a uni call. If you're on N, that's on hook, and H is a hold button, and if you're in a call and you do something, you want a new call and you become connected. And these are events, and these are states, or processes, actually. And that got turned into that. For those of you who know Prolog, you will recognize that as Prolog, using definite clause grammars. And that is pretty much isomorphic to that. And that became that. That's modern Erlang. and there was a transition between that and that in about 1991, something like that. Yeah. And so that, okay, so started off like that, became that became a domain-specific language, that became that, and this implemented, this is the earliest Erlang I can find, and it's 1988. Sort of all the other ones are lost in the mists of time and just didn't bother to keep them. So at that time, you can see it took 4 days to rewrite everything. So it wasn't very big, it's just a prologue program. And I always like this, it ran at 240, an inference per second, that's a kind of function called per second. It ran at 245 inferences per second. And this was a major rewrite, and after the major rewrite, it went to 283 inferences per second and took 4 days to implement it. And at that stage, Robert read my prologue and said, "Can I fiddle with it a bit?" And I said, "Oh, yes, please do." And I think Robert should tell what happened then.
Well, me fiddling is rewriting everything. So yes, I rewrote it. You notice one thing from the film. Of us three, I'm the only one who actually does any work. They're just sitting there talking with each other. I'm the one who actually fixes the bugs. Yeah, so we were coming along. I rewrote the interpreter, and Joe rewrote my interpreter. We did that a couple of times backwards and forwards, and it got better. One interesting thing here, which is that the pipe stuff, that was something we added in, which we thought would help them solve their problem. And it didn't, right? And it was a big, complicated mess we put in there, which we thought they could use, and they came back and said, no, we can't use it because we'd got the problem wrong. So we had to remove it afterwards. We removed it afterwards anyway. That happened a couple of times. We put things in there which we thought would help solve their problem, and it didn't. So gave up doing solutions. But anyway, things were going quite well, and we thought we'd try and make a product of it, which they could use eventually if they were, when they wanted to build a product on it. And a couple of things you have to do to make a product. You need documentation, you need a community, well, you need performance, you need things like courses. I don't have a good slide for courses, but at this time, when Erlang got going, we were basically doing everything. So we were giving courses, not just giving presentations to Ericsson, but also giving courses in Erlang to bits of Ericsson as well while we're developing. So we've had a long history of making courses. And of course, yeah, you need documentation, right, for it. And here is the original documentation for the Erlang system. This is not the code, this is running the system. So we did have documentation for the whole thing, right? That was it. That was very nice. This is from a very early Erlang user conference. I don't know exactly which year it is. It must be early 90s, somewhere around this, where they had Erlang user conferences. And at this stage, they were purely Ericsson things, because Erlang didn't exist outside Ericsson. So we sat in a room there. We used that room for many years to hold the user conferences in. Exactly the same thing. It came more and more people as time went on. Eventually, we filled it. So this is so we did have a community going on, and we had conferences. Once a year, had a conference there. It was in November. It's a very bad month to visit Stockholm if you're coming to Stockholm. So, thank God we moved it this year. That was much better. We had performance, and the performance was, well, flip backwards and forwards, the performance was pretty bad. I think we upped Joe's figures from 280 to about 400 reductions per second using Prolog interpreter, but it was pretty bad stuff. So we had to, the best way of getting past this was doing our own virtual machine, our own implementation. As I said before, been running on top of Prolog, which was very nice for developing the system. You have a lot of tools, have a lot of built-in functionality in the system you can just use straight off. But it also means there are some things you can't do, because you're limited to what the underlying system provides for you. So performance was one of them. And another thing, that we could fiddle with the semantics, what was going on. We had much better control over what we could do with the system. Amongst other things, code change. Okay, now we were actually in charge of loading code, not leaving it to the Prolog system, so we could actually work with code change. This is when having multiple versions of the code came into the system, because we just couldn't do it before. We could play with isolation, and we could look at the problem of having a real-time garbage collector. So these were things we could attack. And how we did it? Well, we did a bytecode interpreter. That was the first version. Got inspiration from the Pascal B machine and from the Warren abstract machine for Prolog. That's what sort of read the documentation for those and got a lot of ideas for how they worked, and tried to do exactly the same thing. Well, tried to do the same thing there. Yeah, we went from poor to much better. Anyway, so this is a basic history, well, very quick history of when we were doing things and about the speed we had. Right? So we had the original interpreters. They were developed in the green and they would be used in the red for doing Prolog. The Strand implementation was one we experimented with. Now, Strand is a concurrent logic language. So concurrent logic languages, they look like Prolog, but they do everything concurrently. They're extremely concurrent. So from their point of view, Erlang has very big, heavy processes. Everything there is a reduction. And we did an experiment with that, of compiling Erlang down into Strand, because there was a commercial Strand implementation. That went quite well. We couldn't do everything we wanted. We didn't get as much speed as we hoped to get, and we didn't have all the control we needed of the system. So even while that was working, we started implementing the JAM. JAM stands for Joe's Abstract Machine. That was Joe's and Mike's hack. We were using that for a long time. Then there came another machine, which eventually became the Beam. I can't remember what Bogdan first called it.
He called it Bogdan's
It wasn't, no, even before they called it the Beam, it had another name. I can't remember what that is.
Bogdan's abstract machine.
Yeah, but before that, he called it something else. I don't know. Anyway, Bogdan was a guy working in the lab, and he was working compiling Erlang down into C, and then running the code through the C compiler, which went quite well. It was reasonably fast, actually. The downside was the compilation took a long time, because I think the whole module became one C function, so it took a long time for the compiler to compile that, and it also generated a lot of code, so it was a code explosion. And we found that the group who were using it, they could not use it. They liked the speed, but it was just too much code for their memory. They didn't have the memory to fit it all in. So it became a threaded interpreter as well, which is based on the same technologies today. Yeah, so improving it, we had the experiments, we did Prolog. Well, that's another parallel logic language. I like parallel logic languages. I think they're fun. We did Strand, we did our own VM. And the compiler and emulator in Prolog, well, the first version of the emulator was written in Prolog, and we're doing about 35 reductions on top of the second that, so it wasn't a direct improvement. It went a bit, but we started doing it in C. And Joe started implementing, writing a C virtual machine, or virtual machine written in C. And Joe is a Fortran programmer.
No, not is a Fortran programmer.
Well, you were a Fortran programmer at those times, yes. And his C code didn't look quite like C. And Mike took one look at that and said, yes, it's the worst program ever. And go away, let me do it. So we ended up, Joe wrote the compiler, Mike wrote the virtual machine, and I did the libraries. So a lot of the things you'll see in the language which people love to hate is my fault. Okay. Yes. Okay. So you're going to talk JAM?
I'll talk JAM, yeah.
You talk JAM, yes.
JAM is Joe's abstract machine, and as I said, Joe wrote the compiler. He first wrote the compiler in Prolog, and he then wrote an Erlang version. You had to bootstrap the compiler the other way, and it was bootstrapped via Prolog compiler. But he was also responsible for the architecture and getting things right. That we went through a number of iterations. I remember the first time it was a register machine we made, and then we went to a sort of more like a Forth-like machine with a sort of threaded interpreter. The VM is not my CV. The VM is written in C. And I thought I knew how to program C at that stage. I'd been programming Unix for a number of years, and I thought I was really quite a good C programmer, a good C hacker, until you actually start writing a virtual machine. And then you realize life is different. That the number of casts and pointers and manipulations and masking of tags, and just a strange thing that if you start using the C compiler, there's things you don't really realize. We're using the Sun's C compiler at that stage. And of course, because it's a bytecode interpreter, the whole main loop is a switch on a byte, which switches to the right instruction. I discovered by peering at the source code that there was no way of stopping that that compiler doing a bounds check on the, or a size check on the byte to check that the byte wasn't larger than 255. So I had to write a little assembly language, a little hack in awk, which munged the object code to get rid of the check, and that made the whole machine suddenly go 15% faster. Weird things you learn. As I say, that if you really want to learn to program C, write a VM. I'm probably better at C than I am at Erlang. The VM is bytecode. The VM at this stage was 32 bits long because machines are 32 bits. I had an 8-bit tag. Incidentally, if you use a 68,000, the original 68,000, that was a 24-bit machine. You didn't actually have to do any operations when pointers to mask away the highest byte. It did it automatically in the hardware, but that was the sort of thing you discovered by mistake. 24 bits data, it's all changed nowadays. The thing we realized is that each Erlang process had its own separate stack and heap, which it still does today. Garbage collection was done per process, and since processes were fairly small, that gave a fairly good real-timeness to the garbage collection. The processes, of course, not only could garbage collection, the stack and heap could vary in size, and you lose a lot of efficiency in actually checking for sizes when you put things on the heap to sort of expand the heap, contract the heap. First version was on the VAX 11750, which I think Joe already mentioned. It actually had 8 megabytes of memory, not 4, sorry Joe. It had about 300 megabytes of disk. I can go on for ages about digital machines if you like. We run Berkeley 4.1 Unix on it. We were regarded by the computer departments of Ericsson as great traitors because we were using Unix, and they were sort of very heavily into IBM machines. And we weren't allowed to put our machine into their data center, so we had to put it in our own little private air-conditioned room with a lock on the door, so that the evilness of digital and Unix wouldn't spread to the rest of the company. First version was on the VAX, then we went to a Sun with a 68K processor. Later we went over to Spark processors. The first product was the one that Joe mentioned, the mobility server. It was then a port to VxWorks. VxWorks is the most horrid operating system I've ever seen. That, I won't go into details about why it's horrid, but I can explain it if you're interested afterwards. Another thing which happened at this stage is that Klacker, Klaus Wikström, came in, and he was the one that actually implemented most of the Erlang distribution. He also implemented Erlang term storage, the ETS system, which is actually the basis of Manesia, and I'll come back to why Manesia is actually important as a database. Erlang spread within Ericsson. We had other products. At this stage, for various reasons, which I will not go into, I was going into management and landed up in a position being the chief architect for a system called ANX, which was Ericsson's first ADSL system. We haven't been very successful in Ericsson selling ADSL systems, mainly because we've had to buy the modem chips from separate external companies, and they charged us so much for the modem chips we couldn't make a profit out of it. The AXD 301 ATM switch is another product which came out. You've all used them. Some of you have probably used an AXD 301 today, without knowing it, because they're actually the basis of BT's telecom network, BT's long distance network. And if you've used it, I'm sure that who's actually used their smartphone to sort of look at a web page today? Who's done that? Yeah? Well, you almost certainly have used the SGS MMME, which is the basis of Ericsson. Ericsson has 45% of the market in mobile data. And you've used an ASN without knowing it. So these things are spread all over the world and are very large. In all these products, the jam was replaced by the beam, which is Bogdan's Erlang engine. Bogdan left Ericsson, and a guy called Björn Gustafsson took over, so it's now Björn's Erlang abstract machine. It's replaced the jam in all products. I think that maybe for historical reasons there are some mobility servers which still use it. I've lost the code, unfortunately. It disappeared somewhere, which is probably a good thing because I don't have to maintain it. Robert did something which you can no doubt talk to him about later. He did Virding's Erlang engine, which was, I think you used reference counting, didn't you?
Well, I did two versions with different. I was experimenting with garbage collection, various garbage collection schemes, to have a central heap and still have a real-time garbage collection. So I did two versions of that. The actual virtual machine is basically the same technology. So the first one was a bytecode interpreter, and the second one was a threaded machine. But I was fiddling with different garbage collection schemes to do that. It actually unfortunately gave a lot less than I had hoped.
One thing you mentioned at the beginning was fault handling and failure handling. You have to remember that in this world there are two different aspects. One of them is faults. Fault is a bug in code, something goes wrong. I'm not going to say how things can go wrong, but the other one is hardware, is failure. And these are fundamentally different because faults, normal exception handling mechanisms in most languages are crap, because you cannot actually handle a fault in the same context as when things go wrong, because you've corrupted your data, you don't know what's wrong. So you have to handle a fault in a different context. And that's the basis of Erlang's fault handling. And it's the same basis of Erlang failure handling, except in Erlang's failure handling, if hardware fails, you cannot rectify a hardware which has failed in the part which has failed, for obvious reasons. Now, the whole idea of error handling actually comes from a very ancient technology which happened in Ericsson, the idea of relay-based telephone exchanges. We had a C-wire, and the C-wire was part of the equipment which controlled all the relays. And it was connected to -48 volts and connected to all the relays which did anything useful. And if anything dreadful happened in the telephone exchange, a little relay contact opened and broke the C-wire, and this caused all the sort of equipment connected to that telephone call to fail. So the C-wire was the idea about how you actually get failure to work. If you have a transaction, you want something to kill all the transactions. And this was the idea which came into Erlang, the idea of linked processes. I made a mistake there. I made processes linked when I implemented them, so there was a dual direction. If A was linked to B, B was also linked to A. Nowadays there's a new monitor called monitor, which does it correctly. So the idea is you have some group of processes which are part of a transaction. If one of them fails, the fault is propagated to all the other processes, and everything fails, except for one or two super simple processes which actually stand there, catch the failure and do something about it. And I said I'd get back to Mnesia. This is actually the primary reason for having Mnesia at this stage was that since processes are too large, you can't have processors for everything. The idea is that you should have a database which was stable and replicated over the nodes, a real-time database, so that every time you go to a stable state in the system, you bung the data in the database, and the database was the basis of recovery. If a transaction failed, you went to the database, got out what is the steady state, and returned to the steady state. So Mnesia is actually, and the concept of using Mnesia as a steady state for recovery is one of the principles of Ericsson's, of Erlang's failure mechanism.
Well, it's an STM, isn't it?
Yeah.
Only before they were invented.
A few things you may not have thought about. I wrote this slide on the plane on the way over because there's a few things people say dynamic typing. Ooh, they're horrible. Can't have that. It actually makes debugging a lot easier because you keep a lot of symbolic information at runtime. And one of the things that happens when things crash in Erlang or things go wrong in Erlang, you want to debug, is you can actually investigate the system and see what happens. You can always look at any data term and find out what it is. I think that Rick yesterday was talking about values and knowing about values. Most data is actually inspectable because you can get out the names of atoms, you can get out the names of functions, you can find, if something crashes, you know exactly which function is crashed and what the data, input data was. It also makes marshalling of data for inter-machine communication easy at runtime. Because you're dynamically typed, you can actually pack everything down to a byte-independent format and send data across a network to another machine. And you don't actually have to specify what the protocol is. I think that breaks one of the principles which Rick was talking about yesterday. Being able to change code on the fly is also something which you don't really think about. That in normal computing, if you go back to C, you have a sort of you think about things, you write a program, you compile the program, you get a segmentation error, you say, oh bother, and then you have to rebuild the system and go all the way around that cycle every time that you go and relink the system. That takes time. It can take 10 minutes in a sort of small system. It can take a whole day in a very large system. The fact that you can actually just reload a code in a running system when something's gone wrong and change the code and correct faults, or even if you like put the equivalent of an IO format, a printf in it to sort of find out to get my data out if you want to, makes debugging an awful lot easier and awful lot thought about. Another thing which is not thought about in Ericsson is that in Erlang is that distribution is transparent in nearly all the code. That if you send a message to another processor, the average bit of code doesn't actually know on what processor, what CPU the process is running. You just bang away a message away to it and off it goes. So having completely transparent distribution is actually important. Selective message reception. A lot of finite state machines have a lot of states. Being able to say what messages you're able to get in which state actually reduces the complex of your state cross message matrix and can actually half the size of code. One of my unfortunate jobs before I left Ericsson was being manager of a unit which made software for base stations, where we were using a product. I like being here now because I've left Ericsson, I can see what I like. That's called Rational Rows. Don't use it. It's horrible. It creates an awful mess that because the way it works there, in any state you can receive any message, which means that one of the most common errors we had was that an unexpected message was received in this state and there was no handler for it, which caused systems to crash. Another reflection I had is that you can implement synchronous inter-process communication on top of asynchronous communication. The reverse is almost impossible. So if you want to do something, do it asynchronously, and then you can make it synchronous if you want, simply by having handshaking backwards and forwards. Don't try and sort of do something synchronous like they did in Ada with rendezvous, and then having to put sort of messenger tasks and all the rest of it to get it right. That's a horrible idea. I think that was my bit. No, this is where we are now in 1992, and I think that it's now Joe's bit, I think, because he's going to tell you, what was it, Robert's bit? I can't remember.
It's my bit, I think.
I think it's Robert's bit, yes.
It's my bit.
Oh, yes, your bit.
My
Go
bit.
on.
Yeah. Yes, it's my bit. Well, yeah, from about 92. Yeah, we were into rapid prototyping and doing stuff as well, too. This is me doing serious work. Okay, it might not quite look like it, but it was. I can't remember which trade show.
It's the MD. Well, we're controlling a train and a telephone exchange.
Yes, that is our telephone exchange, our lab extras there. It was a trade show, I think, wasn't it?
Sorry?
It was a trade show, yeah. We were going to show Erlang there. And say what you like about the MD110, it doesn't really look very flashy to look at, right? I think there's a small red light that goes on when you turn it on, that's about it. There are no blinking lights, no nothing. So we thought we needed something better to show, to demonstrate Erlang. And so what better to have a model train with trains running and the system being controlled by Erlang. So I went out and bought a train set, which could be controlled by a computer.
Is Robert's training system?
What?
Is Robert's training system?
Well, yes. It's my training system. And I wrote an ATC system so I could run trains on it. You could You could plan where you want the trains to go, you could book it, they could reserve paths and things like this and block other things and change the switches automatically. And it was fail-safe, because if something went wrong, it just shut everything down and stopped all the trains, so there are no collisions for it. So that was actually real work, and prototyping that. I think I probably did a bit more than was expected, but never mind, it was fun. It actually worked. I have not been able to find a photograph of the actual system we showed at that show. So we're running, and a colleague of mine, he did a graphical interface so you could show on the screen, you could see where the trains were as they were going around the track and everything like this as well, so you control it. We had to definitely implement a very simple DSL before we knew they were called DSLs, where you could define all these train tracks and how to run. So you could program up sequences of events running through these things to run the train. We could run those. It was a lot of fun, actually. We actually used that in the course, a couple of the courses in Erlang. So you have a sort of an exercise, move the train from one point to another point and stop it when it gets there. Right? So you had to be able to set the switches, you had to be able to read the sensors and things like this for it. They liked that. That was fun. But anyway, yeah. So otherwise, in 92 to 95, nothing much happened. What this means is, yes, a lot of things actually happened. We were doing a lot of implementing in Erlang and putting in new features and making the system better and getting it to work. But in our relations to the company, nothing much happened. There were a few products going on. We were more or less at war with parts of Ericsson, which we won. Well, we did. Well, we did. We were right. And yeah, but otherwise it was relatively calm and peaceful. Until in 95, a big project called the AXEN was cancelled. And AXEN was a project started in 88 to build the next system after the AXE. And we originally asked to join that project. I think we were there for about 6 months before we decided we didn't want to be there anymore. And we left, and we were more or less at war with them, but they died. That was interesting, because a lot of things happened then. We're about here now, in our timeline. And yeah. This is also interesting. I mean, yes, we've got our wars up the top there. Also, our attempts at marketing, they're quite funny, if you look at those. Different ways, we were thinking, how do you sell Erlang? In this case, to the company. So we tried it, calling it functional and declarative, which didn't mean anything to anyone, so basically useless. We came to hide the language. So we wouldn't try to sell the language, we tried to sell the system, or implementation, or very fast, rapid implementation, or things like this. We've got about time to market, interoperability, and stuff like this, and none of it really worked very well. Later, so we got to standard languages. And we're following the standard, which case this was the Erlang standard. So it was quite different. All was standard Erlang. 96, the AXD 301 project was started. That was very good for us and for Ericsson, actually, because as Mike said, this actually was a product that worked and succeeded. And it was made from the leftovers of the AXEN. So it was a very funny project because there were some quite good people there, but it never really got anywhere. This one, they got some of the good people and they made something out of it. And we were working on the AXD 301 project. Of course, we were working, making the Erlang system better so they could use it and depend on it. This was also about this time that the OTP was developed. I mean, we had libraries and things like this before. We had a lot of the philosophy. But OTP was developed around 95, 96, wasn't it, Joe?
Yeah.
Yeah, around there. The OTP group was formed. A group in Ericsson was formed to try and market and support Erlang, still within Ericsson. I think 96 was the year that the first R1 version came out from that. That also meant that we at the lab didn't have to do all this work. Up until this time, we'd been doing all the support and the course and everything for it, apart from in addition to developing the actual language and system. And then 96, 98, well, again, nothing really much happens in the sense that things keep on going. We're developing the system, there come new products, the XD1 is developed, and 301 and works and all this type of thing. And it's a great success. And as Mike said, it's still in use today in BT. So you're probably using it without knowing it. There's trouble with success, right? So there's a bit of trouble with success. You should be careful what happens there.
Creston tells me I have to speed up a bit. So,
Okay, we'll speed up a bit. Yeah.
so we got to here.
Yeah, we had to hear.
And this is very embarrassing because do you remember I was at ICFP? And I stopped the slide at that point deliberately because what had happened actually was that Erlang had been banned inside Ericsson. And we didn't want to tell anybody outside Ericsson because here we're trying to spread it outside Ericsson, but internally it's been banned. And we thought if the people outside Ericsson knew that it was banned inside Ericsson, they might lose faith, you see. So it was a rather embarrassing position of sort of just forgetting to tell people outside Ericsson that it was banned. And that caused all sorts of... Banned inside Ericsson, not banned outside Ericsson. Banned in Ericsson Radio for new projects, but they already had the old projects, so they had to carry on. And that caused an awful lot of stuff to happen. You know these nothing much happens ... Well, banning stuff was actually the best thing that ever happened to Erlang, because a lot of stuff happened. So nothing happened for 4 or 5 months after it was banned. And then guess what? Oh, Erlang became open source. And when it became open source, stuff started very quickly. Because 4 days after it became open source, most of the Erlang people just sort of accidentally left the company and formed a new company. And that was the days of Bluetail. And then things become fragmented. And I'm not going to tell you. Then it just gets so confusing that we don't know what's happening. Because I talked to a consultant once. He said, if you ban something, if you've got something, and the heavy fist comes down, splat, and it splatters. And the seeds go out and they start growing by themselves. So this is the period of great confusion. So I'm going to hop. So 10 years later, 10 years after the ban, well, there's a whole load of books, there's a whole load of... And how these have... Where these are... I don't know where they've come from. I haven't traced it. I haven't a clue. And I can trace the start of it. There's a sort of DNA. It's like Gutenberg, you know, the Gutenberg's, it took 8 years for, 7 years for an apprenticeship, and then another 7 years you had to serve, and after 14 years you were allowed to leave in the Middle Ages, and then after 14 years you split off and you formed. So it's about a 7-year sort of cycle. The lab splattered and it became Bluetail. Bluetail was in existence for about 4 years, and then it got bought up and things happened, and it kind of split mainly into Tail-F and Klarna. I mean, Klarna in its own right is a company of 500 people. Just have to add 100 every time I give a talk. And then, you know, Francesco is a student of mine, you know, and sort of doing his master's. Oh, well, he's gone off and formed a consultancy company, and then it's formed an alliance with Basho, and there's some... lots of other companies. I haven't a clue where they come from or how they started or where these relationships are, and it's all gone daft. And so now time to reflect. What's happened in this period? Well, clock rates went like that. You know, they shot up by, it's a log scale, until 2002. The chips sort of got bigger and bigger and bigger, and you couldn't get across the entire chip in one clock cycle. So, oh dear, speed of light hits you in the face, and they become parallel, and memory sort of went up, shot up like that. And so we got sort of hardware and software. And on the software scale, I mean, Phil's told you about Frege and Curry, and, you know, in 1879, Frege was sort of telling you how to program, but clock speed was 0, and 0 megahertz. And, you know, and Curry came along, and clock speeds were still 0, and there was 0 megabytes of memory. And then round about the 80s, you know, we got 1.6, you know, 1.6 megahertz clock, that was pretty damn fast, and megabytes of memory came. And then round about sort of 2000, 2004, you're getting megabytes of memory, you're getting GPRS, you're getting multi-cores coming in 2004, and gigabytes of RAM, and you've got 4G, you can do gigabytes per second. And things. If you look at this, a heck of a lot of stuff has happened in the last 3 or 4 years. An enormous amount of stuff. It's absolutely amazing. We can do a gigabit per second in the air. You can buy a 3 terabyte disk for, you know, 100 quid or something like that. You will get a terabyte of flash memory in your phone within 5 years. The disk manufacturers, if they wanted to, could give you a petabyte of memory in there, in your disk, on your desktop for 100 quid today, but they're not going to do so. They're going to dribble it out. Every 2 years, you'll buy another disk, and it will be twice the capacity. They could do it tomorrow if they wanted to. So we have to ask ourselves the question, what are we going to do with all this stuff? Well, I reckon this is software. It's like an iceberg, okay? And for a long time, we've been looking at the stuff at the top. So this is what C is. C, up the top, you've got efficiency. And under the water, you've got fault tolerance, distribution, memory usage, garbage collection, latency, distribution, all these sort of horrible things. These are all the things that cost you money. So basing decisions on the thing at the top is absolutely crazy. So what we tried to do is kind of move the bar down, try and make some of these things like fault tolerance and distribution and concurrency and things. Of course, we're not efficient. Efficiency is still down here. But we try to solve all the problems that you have when you're building systems. And the systems haven't got anything to do with efficiency. They have to do with isolation, fault tolerance, scalability, and these kind of things. That's what we tried to do. And I think we were successful in doing so because we addressed those problems first in round about 1985. So we figured out how to, by 1990, we knew how to do that. Of course, we didn't have the hardware to do it on. The multi-cores came along 14 years later, and then they were like, oh, we've been waiting for that to happen, and now we can use them. That was great. So multi-cores are kind of cool, because we just write our program, and, I was in a meeting. Some guys were using a Tylera 64-core processor, and they'd run an Erlang program, and it went 33 times faster. And the managers were going, oh, dear. This isn't very good. Why isn't it going 64 times faster? And I said, well, look, are you pleased that it's going 33 times faster, or are you sad that it's not going 64 times faster? And they said, well, we want it to go 64. I said, how much faster is the C++ project going? Well, it's going 1 times faster, because we can't parallelize it. So anybody here running C++ you're trying to parallelize? Oh, good luck. Sorry, I'm not being nasty about C++, really.
Much.
Right, so tomorrow we're going to have 1 million cores. We'll have 2020, we'll have 1 million core computers. I mean, there are research projects figuring out how we're going to program these things. It will happen. We'll have terabytes of memory in our phones. We'll have gigabits per second in the mobile networks. And we'll have 100 billion connected devices with ubiquitous networking. And today, well, Mike's already said, people think Erlang isn't used that much, but we are, if you're doing data things, if you've got a smartphone, and if you connected up to the networks today, if you used 3G, there would be a 40% chance that it was all set up by Erlang. If you use 4G, which hasn't really written yet, there's a 60% chance, because we've got 60% of the world market there. And it's Erlang that's setting up all those cores. It's Erlang that's put in the part of the system which has to be fault tolerant. And it's been working fine for years. So this is a conference about new languages. And we have new hardware, and we have new problems. So that's why we're here, and I hope you're enjoying it. And I think I'll end there, because I've run over time. And do you have time for questions? Or not?
1 or 2?
1, 2.
No.
No? Okay.
Right.
Well, thank you very much.